So thank you. In this talk, I would like to tell about some aspects of an analog of the Whitney extension problem, but for the space of functions of bounded mean oscillation. This remarkable space, BMO, functions of bounded mean oscillation, has been introduced by Fritz John and Louis Nierenberg in their now classical paper in 1961 on functions of bounded mean oscillation. Let me recall the definition of this space of functions. A function f, which is locally integrable in Rn, belongs to this space if the following quantity is finite. We take for every cube q, usual cube q with sides parallel to coordinate axis, the average of the difference in absolute value of function f and its average on this cube q. This is the average of function f over cube. And if this supremum is finite, this function f belongs to this space, and this quantity is a semi-norm in this space of functions, classical space. So if we refer to this quantity as a mean oscillation of function f over the cube q. So BMO is a space of bounded mean oscillation. Clearly that every infinity function in Rn belongs to this space. Because of these simple calculations, norm of an infinity function in BMO can be estimated by two norms of these functions in L infinity. But not every function in BMO is bounded. The typical example of an unbounded function in BMO is a logarithm of the norm of x in Rn. So this function logarithm plays a very important role in this space. This space BMO has a lot of applications in modern analysis, in various fields of analysis, in particular in harmonic analysis. One of the first results related to BMO has been discovered by Charles Pfefferman, who proved that BMO is a space which is dual the classical Hardy space of functions on Rn. A lot of application of this space one can find in approximation theory, interpolation theory of Banach spaces, complex analysis, probability theory, and so on, so on. And the role of BMO is a good replacement in all these results of L infinity. So many results with the help of BMO can be, and many phenomena can be explained very clearly. So, as I said, we discussed in this talk Whitney type problem for the space BMO. So these are standard questions related to an analog of Whitney type problem for a space. We fix a certain set E in Rn of positive measure and the function f, which is locally integrable on this set. And we ask two questions. How can we tell whether there exists a function f capital from BMO which coincides with function f on E? The first question. The second one, how can we extend a function f defined on E to a function in BMO with minimal norm in BMO? And another, what is the order of magnitude of this minimal BMO norm function? This is so-called trace norm in the space of BMO. We consider all restrictions of functions from BMO Rn to E, and this quantity infimum of all BMO norm of all extension of function f to a BMO function is the standard quotient seminorm in the trace space. So these problems, this analog of the Whitney extension problem, were solved by Thomas Wolff in a bit strange paper. It's actually preprint, 3 or 4 pages, which was never published. And actually, it's not clear what is the year of this preprint, approximately 1986. So this paper actually contains a criterion, a calculation of the trace normal function, which I'll present in a minute. And to extract algorithm is not a very simple task, because actually A solution based of this problem by Thomas Wolff is based on a series of results, rather deep results related to structure of AP weights. Thomas Wolff, he died in 2000 in an accident. I didn't find any other publications related to Van Allen-Whitney extension problem for BMO. So my goal today is to present an explicit construction of algorithm of extension of BMO function for arbitrary subset of Rn of positive measure. So why BMO is so, it may be so interesting for our Whitney problems for spaces of smooth functions. We can say the functions from BMO are smooth functions because the space contains an infinity. But nevertheless, an algorithm of extension of BMO will extend our collections of algorithms of almost optimal extensions of functions of first order of smoothness, which we have here actually two algorithms of such a kind. This is McShane algorithm for extension of Lipschitz functions, actually nonlinear algorithm, and the Whitney extension method. So I'll demonstrate one more algorithm for extension of functions with order of smoothness 1. And the second reason, the space BMO can be included in very natural way in a certain scale of spaces which contains the space Sobolev space W1n in Rn. There is a description of Sobolev space where mean oscillations over the norm in Sobolev space. Such Sobolev space can be calculated as the supremum over all finite families of equal cubes k, and for each such a family we take the sum of mean oscillation to the power n, and this is the norm equivalent to the space. So the norm, if we introduce the scale of spaces, say SP, which defined by similar norm but for a certain parameter p, so BMO is one end of the scale as infinity Rn and Sobolev certain space as nRn. These spaces also can be calculated, can be identified. It's actually some sort of Besov space. But what is interesting for us, these two spaces are in the same scale, and we have a certain positive experience of such approach. For instance, for the space Sobolev W1p, we know that the case infinity actually gives us an extension operator, Whitney extension operator for all the scale. So I don't say that the best, the almost optimal extension operator for BMO will provide an optimal extension for Sobolev, but maybe some features of this operator, some approach may be useful for us, okay? So let me recall a very interesting and important and nice property of functions from BMO space, the so-called the John Nirenberg inequality, which was proven in the paper of John Nirenberg, which states that for each function f in BMO, let lambda be its norm, then there exists a constant c depending only on n, such that for every cube q in Rn and every positive t, the following inequality holds. So we measure the measure of the all points x in given cube q such that the difference of function its mean on this q greater than t, and this inequality states that this distribution function actually is bounded by exponential function with this parameter. And what was proven by Jordan, well, in converse direction, opposite direction, it's also true. If there is a positive constant lambda, so that this inequality holds, then the function f belongs to BMO at its norm is bounded by constant lambda up to some constant c depending only on n. So this is a characteristic, complete characteristic of space BMO in terms of John Nirenberg inequality. And let me, before to turn to traces, and extension to present two equivalent statements which are equivalent to the John-Nuremberg inequality. First of them states that actually the nominal space BMO can be characterized as follows. There exists a positive lambda such that for every cube Q, this quantity is bounded by constant 2. Of course, this quantity is greater than or equal to e to the power mean oscillation because of convexity of function E. So this characteristic is much more stronger, and also in opposite direction the infimum of such lambda gives this inequality. And the second one, actually the John-Nuremberg inequality enables us to measure mean oscillation over arbitrary sets S in Rn of positive measure. So for arbitrary set of S of positive measure, the following inequality holds. So we see that if S is arbitrary not cube, its mean oscillation is bound by ln logarithm 1 plus, this actually is a coefficient of regularity. This is a measure of the smallest cube which contains S up to some constant, and this inequality is true. And they are also in opposite direction. If this inequality is true, then the function F belongs to BMO. Okay, so let me turn to the problem itself, to problem of characterization of traces of BMO functions to arbitrary set in Rn of positive measure, the result proven by Thomas Wolff. His result states the following. A function f can be extended to a BMO function on all of Rn if and only if there exists positive constant lambda such that for every cube Q, the following quantity is bounded by constant 2. So actually we take here the second corollary from the John-Nuremberg inequality, but on the set E. And it turns out that this second form actually provides the criterion for the trace in Rn. In this criterion we can consider only the cubes, those cubes Q whose center belongs to set E. So this is a result of Thomas Wolff. And also, like in John-Nuremberg inequality, we can reformulate this result in terms of equivalent criterions. First of them is precisely the John-Nuremberg inequality on set E. So this an equivalent criterion which states that the function f can be extended to BMO function if and only if on the set E the John-Nuremberg inequality is satisfied. And also another equivalent criterion states that if bounded oscillation of over all sets S of positive measure, subset of set E are bounded by this quantity, this function can be extended to a BMO function. So this is criterion for the trace description of the norm of function f, trace norm of function f. Infimum of this constant lambda in all this criterion is equivalent up to some constant depending on n to the trace norm of function f in BMO. Okay. So, but now let me demonstrate the extension algorithm, which I think looks for us a bit mysterious. So let's see what is the extension algorithm. So given a function g on set E by this sign g wedge, curly wedge, we denote its extension by 0 to all of Rn. And as usual, mhx given a locally integrable function x denote the classical Hardy-Littlewood maximal function. So fix an arbitrary non-negative function in L2 Rn, which is whose support belongs to E, and this function is not identical to 0 function. So it means that for some set of more positive measure in E, this function is positive. Okay, so I present this criterion in next two theorems. So the first one, theorem 1, states the following. Let f be a local integration function such that the Wolff criterion is satisfied. Let us introduce two operators on Rn. T1 and T2, which we calculate as follows for a given function f h locally integrable in Rn. First, we consider function e to the power minus f over 8 lambda, and we take its extension by 0 on all of Rn. Then we multiply this function to function h and calculate its maximal function. And then we multiply this maximal function by e to the power plus f, not minus plus, and extension of this function to on all of Rn by 0. So this is the first operator T1h. And the second operator, we change the order of plus and minus, actually. Here we take with plus, here with minus, but the same construction. The theorem states the following. There exists a positive constant gamma dependent on ln such that the next operator, this mapping, is a contractive operator in L2 with constant half. So for every two function h and g in L2 Rn, the distance between s, h, and g is bounded by half distance between h and g in L2. And this is the first theorem, which we will use in our algorithm. I'll prove this theorem later on. So because this operator is contractive, there is the unique fixed point of this operator, a certain function h depending on f satisfying this condition. Using this function, we define the extension operator as follows. This is actually theorem 2, which states that under Wolf condition, the following function, this is an extension function f, by this bit strange formula, we take the same operation. We take function f e to the power function f over 8 lambda, its extension by 0, we multiply to hf and calculate maximal function, divided by the same operation, although with the sign minus. We take ln, multiply to this number, and the theorem states that this function, this extension, belongs to BMO-Rn, and its norm in BMO-Rn is bounded by constant lambda times some constant dependent on n. So this is an extension algorithm. First, we fix the function hf as as the fixed point of this strange operator s, and using this function we define the extension. The question why this is extension, how it can be proven. Actually, the proof is rather short, and I'll try to demonstrate this proof in this lecture. So actually, all steps of this proof I'll show today, besides two results which can be found in the literature. First of them is the result of Mackenhaupt, classical result about maximal function and A2 weight, and the second one also more or less classical result due to Koif and Rorbeck. So let us begin the proof of this result. First of all, I need definition of the so-called A2 condition for two given weights u and v. So u, v, two non-negative function locally integrable on Rn. And we say that these pair functions satisfy A2 condition if for every cube q in Rn the following condition is satisfied. So this expression times this one is bounded by constant 2. Actually, in the literature is bounded simply, but for our purpose we need 2 in the right-hand side. It is very well-known result due to Mackenhaupt. If u and v is the same, that the maximal operator is bounded in L2 with respect to this weight. But in our case, u and v are different, and so such sort of result is not true. But if we will take function u and v in some power which is strictly less than 1, say in half, the result which is analog of this classical result of Mackenhaupt holds. So this theorem actually, which can be found in Mackenhaupt paper, states the following. Whenever u, v is A2 weight, then the maximal operator with weight v to the power half this operator maps L2 with weight v to the power half to L2 u to the power half. And the same, of course, by symmetry is true to the power minus half, but u and v change places. And in both cases, the norms of these operators are bounded by some constant dependent only on n. This result due to Mackenhaupt, which can be proven on one page, I think. Okay, so using this, so this is actually a result which I meant in the previous theorem, which states that these two inequalities are satisfied. But using this result, we can now define two operators, tau1 and tau2, using this formula. We take an arbitrary function h multiplied to weight v to the power minus 1 over 4 and times u to this power, and we change directions of plus and minus, and function uhv, two different operators. From this theorem, actually, using this inequality, we immediately obtain that both these two operators are bounded in L2 with weight 1. And it's precisely the same. And the operator norm of these two operators are bounded by some constant dependent only on n. Okay. So now, let us consider now, this is a general result. Now consider given function f two weights. One of them is weight u capital. This is the function which equals to this quantity on set E and 0 out of set E. And this function v capital is the same function, but we extend this function to all of n by plus infinity. This is all the difference. It's not a big problem with v with plus infinity, because actually later on we use actually 1 over v, so we have no problem with well-defined, not well-defined. And the first result, if this condition is satisfied, then this pair is A2 weight. So provided this condition is satisfied, this is more or less standard in the theory of BMO function and to weight. Here is very short and simple proof of this fact. We have to estimate so this quantity which we obtain from the definition of A2 weight. So let us estimate to the power half. So actually this expression, so using this inequality between geometric mean and arithmetic mean, we obtain this. This guy is bounded by this quantity times e to the power minus f. Mean f on q is a over to lambda, and the same with plus. It's nothing more than inequality between geometric mean and arithmetic mean. And we can estimate now that this is precisely this expression, which can be each function can be bounded by function with absolute value. Okay, so instead of half, we take here absolute value and we obtain this constant 1. So actually we have obtained that this quantity is bounded by this mean value, this average, but let us, using Hölder inequality, instead of this norm, we estimate by this average by norm in L2, and we precisely obtain what we need, because this guy is bounded by 2, we obtain square root 2. That's what we need precisely. This quantity is bounded by 2. This is all the proof. So every BMO function, every function satisfying the Wolf condition in a natural way generates two weights u and v, A2 weights. Okay, so now let me recall that in our definition of extension, we have introduced two operators, T1 and T2, by this formula. Precisely T1 is, with respect to u and v, can be written as in our general lemma, our general definition of operator T1, tau1 and tau2. So the same operation. This is the definition of T1 and T2 where this function u capital and v capital. And we know by lemma 1 that whenever this pair is A2 weight, these operators are bounded in L2 precisely. And norms of these operators are bounded by certain constant gamma 1 depending only on n. So this proves that this operator S, which we have defined earlier, is actually operator which is bounded in L2. But furthermore, this operator is contracting operator with this constant, satisfy Lipschitz condition with respect to L2 norm, whenever gamma is actually for gamma 1. Why? The proof is very elementary. The maximal operator is a sub-additive operator. So for any two function NG, the difference between MH and MG can be estimated by maximal operator of their differences. So because this operator Ti can be expressed in terms of maximal operator, this operator also satisfies this property, which follows from a definition and this property of function, maximal function. So it's proved that the distance in L2 between Tih, Tij is bounded by L2 norm of Tih minus G. Because this operator is bounded, this can be estimated by gamma 1 distance between A and G in L2. And so taking gamma to be for gamma 1, we have that this operator H S satisfies, it immediately follows the Lipschitz condition in L2 with constant half. That's all. So this is the proof of theorem 1. Okay, now we turn to the problem, to the theorem 2, which actually justification of the extension algorithm. The proof is based on a remarkable result due to Kaufman and Rockberg, which states that for every locally integrable function in Rn, such that its maximal function is bounded almost everywhere in Rn, the following inequality holds. So we take maximal function, ln of this function, and it turns out that this function in BMO, and moreover, its BMO norm is bounded by some constant dependent only on n. So ln of maximal operator actually maps a locally integrable function into the certain ball in BMO. That is the result due to Kaufman and Rockberg. Now the proof of theorem 2. Let me recall that our extension is given by the following formula. Function f coincides with function f capital coincides with function f on E. And outside of E function f, this is the following function g, which we define by this formula as ln of ratio of two maximal functions. So let me recall also that the function hf satisfies as a fixed point of operator S satisfies this equality. hf is the solution of this equality. First of all, let's see that this operator is well defined. This quantity is not zero for every function f. This immediately follows from the fact that the function u0 is positive on a certain subset of set E. Because function h greater than this function, it also is positive on subset of set E of positive measure. So this quantity, which actually defines the extension, is positive. Because of that, is the reason why we use function u0 in the definition of the operator. So now we can easily prove that. So our aim is to prove that BMO normal function f is bounded by some constant dependent only on n. Using Kaufman-Rockberg result, we immediately prove that the normal function g in BMO is bounded by some constant. In fact, actually, this norm can be estimated as BMO norm of ln of maximal function of this function plus the same of this function. We know that BMO norms of these two functions are bounded by constants, so BMO norm of function g is bounded by some constant depending by constant lambda times some constant dependent only on n. But g coincides with f outside of E, but does not coincide on set E itself. But we will immediately prove this theorem 2 if we shall prove that the distance in L infinity in Rn, it's actually enough for us L infinity in set E, because these two functions coincide out of set E, is bounded the same constant lambda times Cn. Let's do this. It very elementary follows from the construction. Why? Because we know again HF is the solution of this equality. So we see that HF is actually greater than or equal to this quantity, right? Because all items are non-negative. So H is greater than or equal to this quantity, but of course H less than or equal to this function. Why? Because maximal function is less than or equal to function itself. But if we write down the inequality, we immediately obtain that this quantity greater than or equal to H, right? Because this sign plus, this minus, we obtain H. This is property of maximal function. So now, if we take the ratio of these two expressions, we obtain this inequality. This is equivalent to this inequality. This guy is bounded by this guy, and we obtain this inequality. And taking logarithm from both sides, we immediately obtain that the function g is bounded by f plus 4 ln of gamma lambda. That's what we have from the equation for the function h. And in the same way, we prove that the estimating estimating e to the power plus f from this equality, we obtain inequality from B rule for function g. It's less than or equal to f minus 4 lambda, which gives us the required inequality that the difference between g and h on E is bounded by this constant, and this is precisely this fact. So now estimating norm f and BMO, we see that it can be estimated by norm g in BMO and norm of this difference, but because this function in infinity is 2 times norm in infinity, which is bounded, and that's it. That's the proof. So, I have 10 minutes, right? Okay, so let me present some remarks related to this result. It's completely new for us, I think, such sort of algorithms for functions of first order of smoothness, something very unusual, something mysterious. So this is actually, I recall the algorithm which states that under this condition, we introduce function, we extend function f by this quantity whenever function h satisfies is the fixed point of this operator. My first remark relates to the operator s. Actually, the formula of this operator can be slightly modified, slightly simplified. Instead of these two operators, we can consider slightly more simple expression. We can take, we can fix x and consider this function as like it's function of y. Okay? So we take this function on set E and extend by 0, multiply by function h depending on y also, and calculate maximal function with respect to y. And multiply by characteristic function on E, and the same operator as wiggle leads us to the result. So this is slightly simpler expression for the operators. My first remark. My second remark relates to extension algorithm itself. So we have a function hf as a fixed point of certain contracting operator in L2. It's very well known. Banach principle, this point can be obtained by iteration of this operator. So these iterations, here iterations actually of this operator, and we obtain hm plus 1 by this formula. And it is known from the course of functional analysis that these iterations tends to the fixed point very rapidly. So we can organize for each iteration corresponding function fm, like an extension of function f, but with certain iteration h. We know that this guy tends to a function h very, very fast, but to estimate how fast function f tends to the extension is not a simple task. Maybe to our next conference in Banff I'll bring some calculation about that, but it's not trivial. Okay, and the second remark relates to the existence of a linear extension operator. We study this to Whitney-type problems for the existence of a linear extension operator. Given set of positive measures, does there exist a continuous linear extension operator which maps the trace of BMO to E to BMO itself? So I conjecture the answer is negative. There is a set E of positive measure even in R such that the extension operator does not exist. This operator, which was demonstrated, is of course nonlinear operator, very nonlinear. And maybe the next example, the next set E in R is the potential candidate to this role such that the extension operator does not exist. The structure is very simple. So on every segment m plus 1 on the real line, we take a division by this segment to m equal subsegments. And on every segment, subsegment of length 1 over m, we fix a segment whose length is certain small number em, such that em over m tends to 0 whenever m tends to infinity. So it seems to me for this set, there is no linear extension operator for BMO functions. Why? Because whenever we will consider this certain part, this set, and we'll try to answer the following question: does there exist linear extension operator for this simple set? Well, this set m plus 1, and our set in the red color, whose norm does not depend on this ratio. It seems to me the answer is negative to this problem. Why? Here are some speculations about that actually for this simple set, the problem can be reduced. Fortunately, I have no time to show how it can be done, to calculation of the so-called E-functional for the couple BMO and L infinity. This is a very important object in the interpolation theory, whose definition is as follows. We take a function f and we take best approximation of this function in the norm BMO by L infinity functions whose norm is bounded by t in L infinity. So it actually can be shown that the problem of calculation of BMO norm for set E is equivalent to the calculation of the E function for this particular set EM from this picture. But the problem of linear extension operator also can be reformulated in terms of real interpolation theory. So unfortunately, I have no time for further explanation. So actually, this leads us to the following natural question, which is very close to problem of existence of a linear extension operator for BMO functions. Question is as follows: whether the space L infinity R is the complemented subspace of BMO R. Apparently, the answer is negative. So if it's not it's positive, that would be something sensation answer. And this is very close to this problem. So that's my thoughts about why this example can be a candidate to the role of a set where the linear extension operator for BMO does not exist. So how much time do I have?
About 3 or 4 minutes.
How much?
About 3 or 4 minutes.
Okay. So one more remark. Actually, I have no time to present more slides. It turns out that for sets in Rn which are rather massive, say like regular sets or n-regular sets, set E is n-regular if for each cube Q centered in this set, the measure of intersection with this set is bound, you measure the measure of set Q with where theta is certain given constant greater than 1. For such sort of set, there is simply characterization of traces of BMO actually the same like in definition of John and Nirenberg, and for such sets the linear extension operator exists, and this collection of sets can be extended, but my time is over, so thank you for your attention.